Hello, let us continue with discussing trade-off between time and memory, and we continue to consider sorting algorithm as a sorting problem, as a model problem. We have counting sort that have linear time complexity if range between maximum and minimal elements are very small. We have selection sort and bubble sort that have a square complexity, and they don't depend on range between maximal and minimal values. But these sorting algorithms have constant memory complexity. We have quick sort that is much faster than existing ones. It has n log n time complexity, but in worst case, it is n square. And if someone attacks you and suggests a special constructed data, you can have n square time complexity. And you have memory complexity from log n in the best case and average case as n log n for time complexity. And in worst case, the memory complexity is O from n because of memory complexity for recursion when we store information in stack. Okay. Today we consider some different idea for the sorting. So firstly, as a quick sort that give us a faster version of bubble sort, we consider another slow sorting algorithm that called insertion sort, and after that consider improvement of this algorithm with better time complexity that doesn't depend on worst case and best case and so on. And in worst case, it has n log n time complexity. So let's start with insertion sort. Insertion sorts have the following idea. If we already have sorted part of the array from 0 to element m, then we want to obtain new little bit bigger sorted part of array that from 0 to m plus 1. If we can do it, then we just add elements one by one to sorted part, and in the end you get the sorted algorithm sorted array totally. So how we obtain the sorted prefix or sorted part from beginning? So firstly, we can say that A0 is already sorted. The element on the single element is already sorted part of array. So what next? If we add A1, then we can just swap them if it is required for obtaining sorted part of two elements. So what next? We add A2. Then we have sorted part from A1, 0, A1. We can insert it there. What does it mean? We just swap. We, as in bubble sort, we check A1 and A2. Which one is bigger? If A1 is bigger, then we keep it on this place. If not, we swap it and move it to the left. And we move A2 to the left until it is still smaller than the previous element. And when it is already on their place, then we obtain sorted part from A0, A2. The same idea for A3. We swap it to and move it to the left until it becomes to the right place. It means that it is such that A3 is bigger than the previous element. So it is similar to bubble sort, but we don't go from left to right and put element to the right, biggest element to the right place. But here we go from right to left and know that we want to put a new element to the right place. Here we continue with A4, A3, and so on, and until m+1, move it to some position that is correct position, and do it until we come to n-1 that came to the right position and obtain the sorted array from 0 to n-1. Okay, let's look to some example. We have such an array. Firstly, A1 on the right place, it is already sorted part. So A1, so this one value is already sorted part, that is A0, sorry. And we add A1 and put it on the right place. Okay, it is already on the right place and it is already sorted part. So we look to this element 2 and move it to the left until it becomes to the correct place, that is here. Okay, we move 3 until it comes to the right place here. 5 until it came to right place. It's already on right place. Okay, good, and so on. And for each element, we compare from previous one. If it is bigger than previous one, we swap it. If it is bigger than previous one, we swap it, and so on until it is incorrect. So we get false for this condition, and it is already a right place, and so on. So we go from 1 to n, that is adding element, and until the condition is true that the current element is bigger than the, less than the previous element, then we swap them, yeah, or until the element comes to the zeroth position. So what about time complexity and memory complexity of this solution? As it was for bubble sort and also for selection sort, in worst case, we go from right to left for each of this element. So for insertion on right place, in worst case, it is sorted in opposite order, and we should move elements to the beginning. Okay, in that case, complexity of the inner while loop firstly is 1, then 2, then 3, and so on, and -1, that is sum of arithmetic series, that is n squared, or arithmetic progression. So, but we can see that if array already sorted or almost sorted, in that case, we shouldn't move too much elements to the left, and in the best case, complexity of the solution is linear ON. And memory complexity also here constant. You can see that we use only several variables, don't use array, don't use recursion, and so on. We have one more sorting algorithm, insertion sort algorithm, that is somehow modification of bubble sort algorithm, we can say, but it is little bit another point of view. So it is a mix of selection sort and bubble sort and give us a new idea. Let us try to consider a fast version of insertion sort algorithm. For this goal, we try to use balance. We remember that in quick sort case, we try to put element on the some middle element by value and split our array to two parts and recursively do the same idea for left part and right part. And the best case was when we split it to two almost equal parts. So we try to do to keep this balance, and we try to split elements our array to two equal parts, and use this idea for sorting for sorting algorithm and try to keep these parts exactly equal. Okay, we firstly discuss some additional problem that called merging two arrays. So assume that we have two arrays that already sorted. What we want to merge them. We want to put two new array that have lengths, sum of lengths of these two arrays, and contains all elements from these two arrays, but it should be also sorted. So assume that we have array A and array B. The final array should be this one. And for example, if 5 occurs twice, once in first array, second once in second array, then it should be twice also here. How to do it? So firstly, we can see that here should be minimal element of all of them. So we know the minimal element from the first list is the first element. The minimal element from the second list is the first element. So we can say that minimum element of all elements is the minimum of two of these first elements. We can write the minimum of them. So next we should put minimum of these elements except the element that already see. The minimal element from the first list except the first element is this 5. Yeah, it's the next element compared to this one. And here still the element, the first element in array B. We choose one of them, minimal of them, and write it. And so now we can consider the minimum of this element. So what we do, we have two pointers. First pointer on the array A that show the minimal element from the elements that are not considered yet. The second pointer from the second array, and it shows the minimal element from elements that is not considered yet. And we move them. We choose the minimal from these two pointers, and after that we move this pointer to the next position. So how we can do it in several ways. One of these following one. The minimal element in the first array is I, and minimal element on the second array is j, and k is the index of element when we write the answer in array C. So we do the following steps until I and j is not in the end of their arrays. So firstly, we check if element in the first array is smaller than element in the second array, then we write this element to array C and increase both pointers I and k. So the same for opposite case, we put element from B to C and increase these two pointers. And if we still have some elements in array I after this process, it means that array B is finished. Then we write all rest elements from array I. And similar we do with array B. So let's look what is the time complexity of this idea. The time complexity is n plus m. Why? Firstly, we can see that for each step of this while or this while or this while, k is increasing, k plus plus. The maximal value of k is n plus m. So that's why we can see that there are exactly n plus m steps. Another idea how to understand it, we can see that on each step, I increase it or j increase it. So totally, these two pointers can be increased n steps for I, j steps for m. Only one of them is increased for one step, then the total number of steps is sum of them, n plus m. Okay. What about, let's look to the modification of this problem, where we have one array with two parts. First part is sorted until index m from L to M, and second part also sort from n plus 1 to R. We want to merge it and put it firstly to array C from same indexes L to R, and then replace the part of array from L to R by this sorted part. It means that after this process, if part of array from L to M is sorted, from M plus 1 to R is sorted, then we replace it by sorted total array. Okay, let's look to the example. If we have the first part already sorted from 1 to 12 and from 3 to 14 also sorted, we try to merge them to sorted part of array. Okay, we want to have such merged part to MC and then copy it back to here. We can use the same code, but use only array A for instead of B. So on the array A here, and for indexes, you can use I and J. And J is from M plus 1 and I from N, and end of I is M and end of J is R here. So, but after that, we copy from indexes from L to R back from C to A. Okay, what is the time complexity and memory complexity here? Time complexity is R minus L because it is sum of lengths of two parts from L to M and from M plus 1 to R. The total length is R minus L. But memory complexity, we can say that also R minus L because if we our goal is to have the merged sorted part of A from L to R, then C is additional memory complexity. So complexity is R minus L. In fact, we can use not the total RC, but just part of array from L minus L. In that case, we don't use such indexes, but from 0 to R minus L here. Okay, so totally we can use this idea for merging. Yeah. Is like insertion sort. We don't insertion sort is like merging two parts, one element sorted element and already sorted begin. Here we merge two longer sorted parts of array. So we want to sort array from O to R. What we do? We sort the left part, the right part separately, and then merge it. Yeah, if they are sorted, then we can merge it. So we do it. We split the part from L to R to two parts with equal length. We sort the left part, right part, and then just invoke merge. So for sorting this part, it is the same if it is merging. If we split them to two parts and merge each of them separately and then merge it. So on until we get the element array of single element where L is equal to R. In that case, we stop. Okay. We sort each part separately. For sorting whole array, we sort it from 0 to n minus 1. Okay, what is the time complexity of this solution? We can say that merging for two equal parts of whole array is n. For each of them, we split it to two parts, exactly two parts, exactly two equal parts, not like in quicksort, but you can see that we split it by index. That's why it is exactly two parts. So we have n over 2 n over 2 here, then over 1 over 4 n over 4. Each of them we also split to two exactly parts. We have such balance until each of elements is of size 1. So it is the same. We have k faces and complexities and time scale like in quicksort analysis. And because this should be 1, so the k is log n, so the total complexity is n log n. What is the memory complexity? Here, memory complexity is linear because we need additional complexity for merging, and in the first step, the memory complexity is already linear because we should have whole array for merging additional array. So finally, we get a solution that have exactly n log n complexity in worst case, but memory complexity always is linear. Thank you for watching this video.